Now, concept for the shuttle. Reusability equals low cost. That was fundamental. Everybody believed that. We had studies done by all sorts of outside groups, IDA, the Aerospace Corporation, and others that did studies that essentially agreed with us that there'd be a terrific reduction in the cost of getting stuff into orbit if we would build a recoverable vehicle. Now, it was clear that since the R&D, RDT&E costs are higher, that you need a whole bunch of flights. In other words, if you had a few flights, the extra R&D on the shuttle wouldn't pay off because you could build cheap ballistic launch vehicles that would pay off before the shuttle would. So you need a lot of flights for a recoverable vehicle to be economical. The lower the R&D, the less flights needed to be better than the ballistic launch vehicles. And if you got a lot of flights, because the flight costs are so low, then a two-stage fully recoverable system would be the right way to go. Okay? That was our concepts of what we were dealing with in the shuttle. There had been a lot of technology. I don't know how many of you know that the early lifting body was done by a guy named Brunelli. Not Bernoulli, but Brunelli. Brunelli was in Long Island, and he built a, I wonder if it's my next slide. He built a, first lifting body. That's an airfoil section, and that's a broad piece of fuselage, wide enough that the two engines could be involved in it. Big windows for transport. It was really quite an interesting beginning of a cargo airplane. In 1921, he built one of them, and that was the end of that. But there were a lot of other things going on. You know, after Sputnik, the United States just kind of went wild with ideas for a while, and then settled down on having NASA put in place, decided that the military dinosaurs and mole programs wouldn't be done, that NASA would take over that kind of activity. And but we got some really interesting stuff going. HL-10 lifting body, the X-24A lifting body, the X-15, although that was not considered a space device, really did end up with, by the time they put external tanks on it, got up to Mach 6 and, 300,000 feet. Really some terrific performance out of that airplane. And then I added the Navajo, which I worked on for many years, because it had a parallel tank separation at Mach 3. It was the booster was under the vehicle. The vehicle was a ramjet vehicle, and it separated to Mach 3 at about 40,000 feet. So it was a high dynamic pressure separation. But it showed us that parallel separation would work, and that gets into this picture later. So next step was in that 69 to 71 time period, there's a guy named Max Faget, who is a really important, almost a genius in my mind in design, that did the original Mercury and Gemini capsules, physically designed the shape of the Apollo command module, and then came up with this first sort of practical view of a two-stage fully recoverable system. It had straight wings, like an X-15. In fact, if you looked at the plan form, it looked quite a lot like an X-15. And but it had two of them. It had pilots in each of the two stages, and had internal fuel. It had metal shingles, what I used to call unobtainium, but it was like molybdenum and Rene 41 and some really interesting materials which were really difficult to handle, stress corrosion problems, all kinds of things that were tough to handle. And that's why I talked about unobtainium or some ablative. And Max expected to have to use ablative on the leading edge of the wings And it had varying payloads. The highest one I saw in any of the history was 20,000 pounds, but 14,000, 20,000, that kind of thing. A payload bay of about 12 by 40 and 400 miles max cross range. This gets important in requirements. And at that time, because we were going to have all these space stations and go to the moon and all that sort of stuff, we were going to have 100 to 150 flights a year. And that gets, if you have a lot of flights, it overcomes the base cost of the RDT&E, and he was getting down into the $5 million a flight in his estimates. But meanwhile, because we had lost the space station, we had lost the lunar base, all this grand plan had disappeared, we needed more payloads. We needed to get up to the 40 to 50 payloads a year to be able to make the shuttle look economic at the levels of cost effectiveness that the Office of Management and Budget was demanding of us. After this vote in the Senate, George Lowe decided that we had to be responsive to the OMB, so we had to get some more flights. And this is where our requirements began to come into the picture. We spent about a year working with the military, where they finally agreed they'd put all their payloads on the, and I mean all their payloads on the shuttle, if we could meet the cost estimates that we had. The commercial people were eager to get on the shuttle if our costs would be this low, because they were beginning to see launch costs equal to or more than the cost of the satellites they were putting up. And the science people bought into the idea of space servicing. This really got important because they agreed to design the Hubble Space Telescope so that it could be serviced in space. And that turned out to be, of course, the key to the shuttle, to the Hubble, because of the mistake that was made in the mirror. The resurfacing of the Hubble Space Telescope is what, by bringing another optics in front of this distorted mirror, brought the Hubble back to the fantastic performance it has today. And so,
question to that one.
Yeah.
On that, in your opinion, was the science community really anxious to have the servicing, or was it something that was really forced upon them to increase the constituency?
I think originally they thought they were being forced, but as they thought it through, they could see that they could later change sensors and add additional stuff. And at least I know that the head of the science group, wow, I can't think of his name now, enthusiastically supported it and got the system out there to support that idea. And they worked very closely with us on how to design it so that you could get access to the thing in space. You know, with all the difficulty we have with gloves and so on, they worked to help us understand how to remove and replace systems, and so they did get.
Was there at that time, if you recall, an opposition from the space science community to the amount of the size of the NASA budget that was being spent on the shuttle and on the manned program?
Oh, absolutely. Yeah, there was. Yeah, and but on the other hand, some of the committees, like the town committee, supported the shuttle because they could see other science opportunities that were involved. So it wasn't a, you know, they didn't gang up on us. It was they were shooting arrows at us here and there. So that brought enough. Oh yeah, then let me go on with the requirements. Because of the military requirements, we had to change our specifications. And this became another one of the elements that drove the final design. Military wanted a 60-foot long payload bay. It had been 40 in the designs that we'd been doing so far. They wanted 40,000 pounds polar. and that made our due east payload up to about 65,000. So that was a big change from 20,000 to 65,000. And they needed 1,500 cross range. They wanted to be able to go around the Earth while the Earth turned and land at the same spot. So they had to have 1,500 miles of cross range. Now you could do it a lot of different ways. You could carry turbojets when you came back in and fly it back the 1,500 miles, or you could do it without turbojets, which means you have to have aerodynamic cross range while you're coming in. Payload bay increased to 15 by 60. 15 was an increase by NASA because they saw that they didn't have a Saturn V anymore to do space station. So the best they could do is increase the diameter of the shuttle to where they had a 15-foot diameter to where they could carry the sections of a space station that we are now have in our program. We thought anything less than that was just too cramped for the guys. We decided we would find a non-ablative reusable thermal protection system. Technology had moved far enough by that time that we were beginning to see these ceramic tiles develop to the place where they looked feasible. They had been able to find a hardening for the surface that made them less penetratable than they had been. And carbon came in that we could use for the leading edge for 3,000 degree leading edge temperatures. We followed the tradition that said if it's fully recoverable, it's going to be cheaper. So let's go for a two-stage fully recoverable system. And of course, all the other things that we were developing at that time to reduce the cost of operations with automatic checkout and so on. Well, that's a bad picture of, and I never was able to get that thing. I'm not an expert at this stuff, so I wasn't able to get that slide down far enough to show where the Saturn V was, but Saturn V is only about 50% longer than that upper stage there. So this thing had gotten big, and the booster was larger than a 747, had to operate up to about Mach 6. The orbiter was about the size of a MD-80, MD-90, the twin-engine small transport. And so they were big. And these things had 12 big high-pressure engines in them. And we in management, and I think the guys in design, were getting pretty worried about whether an airplane that large at that Mach number was going to be a practical thing in terms of a system. Now, that's not a system engineering approach. That's sort of a gut feeling that you get after being in the airplane business for a lot of years and watching the development problems that were involved on the X-15, for example. How long it took the X-15 to get to where it could go to Mach 6. But that was the direction we were going. By the way, one of the companies had the wings on the orbiter turned up for, I don't know why, but they had them turned up. The rest of them generally, oh, and by the way, the reason you see two different configurations here is in our Phase B studies to the industry, we said, design us one that only has 400 miles cross range, and design us one that has 1,500 miles cross range. The upper ones have 1,500 miles cross range because the delta wing will do that. The straight wings won't. And so as we developed these requirements, it became clear that we were not going to go with a straight wing system. So these Phase B studies that we had showed that we were going to have a development cost of someplace between $12 and $15 billion for R&D. And about that time, Nixon had a meeting with Fletcher and said, you can build any kind of shuttle you want as long as it only costs $5 billion. Well, that was a big shock to the system. And OMB said, having heard that, OMB says, make it cost effective. And that was a real tremendous driver in the system, because we had never been asked to do that before, and we had a whole new set of requirements to try to deal with. So we had this Phase B program. It was almost complete. Had all these big, beautiful configuration studies, and we had to look again. So we went out and said, let's get imaginative, guys. Let's see if there's any way that we can reduce the cost. There'd been enough going on where one of the companies had been looking at the possibility of putting external tanks, like drop tanks, on the top of the wing on each side. There were two of them, one on each side of the orbiter. And it made the orbiter itself, of course, much smaller. Remember, we're carrying hydrogen and oxygen, and we were doing it inside the vehicles in those studies you saw in the Phase B. And so it grew the outside dimensions tremendously. And by going external with the fuels, it really shrank down the system to where the diameter of the payload compartment was essentially the diameter of the orbiter. And so people began to look at other ways to do it. We had guys coming in talking about single stage to orbit, and that was one that I rejected without study, because I knew that the mass fractions required for that were just out of the world of reality. There was a thing called a trimes, where the theory was that you have three vehicles, two of them were, and they were deltas. They fit together in a nice little teepee, and two of them would be used for boosters going up, and the third one would go on into orbit. And that was kind of a dumb idea, because it turns out boosters and orbiters have entirely different requirements, and so they might look the same on paper, but they would not be the same when you build them. Lockheed came in with an X-24B, which had tanks mounted up forward of the delta wing. And the idea would be that they would peel off after fuel was fed to the main engines in the orbiter itself. And then we began to see these external orbiter tank studies. And when the tanks began to look good externally, then the question is, do you boost from under the tank, or do you boost with two boosters parallel to the tank itself? When the tanks went external, it finally ended up obvious that you'd want one tank instead of two. So the one tank went underneath the orbiter. Then the question is, do you boost through the tank, or do you boost in parallel to the tank with two attached boosters? So we had all these different studies, and what was happening in the administration was they were kind of locked up with reducing manned spaceflight budget down to like $1.5 to $1.7 billion. And we needed to do this cost effectiveness study for OMB. We hired an outfit called Mathematica, which had a senior, well-known economist named Morgenstern, and a bright young guy named Klaus Heiss, who did a study for us on the cost effectiveness of the shuttle. And to make a very long story short, the results were that the present configuration that we have for the shuttle today is the one that looked the best. The present configuration being an orbiter with a tank under it with the hydrogen and oxygen in that tank, fed separately into the orbiter and to the main engines, which were so expensive that we wanted to recover them, and boosters being solid rockets attached to the tank, so that the total vehicle was a little shorter. Important point. At that time, the solids were recoverable. Their wall thickness was enough that that you could use the solid rockets, drop them off by parachute into the ocean, pick them up, bring them back, clean them out, and use them again. And that was going to be a cost saving in the program. And by doing all this, we had liftoff thrust augmentation with the engines in the orbiter. These engines, by the way, were 12,000 pounds per square inch internal pressure engines, staged combustion, the most advanced technology you could imagine. And they were started a year before the shuttle was started to give them more time to develop. They almost became the long pole in the tent. But I think maybe when it finally boiled down, the thermal protection was the longest pole. He was down there trying to fix them. I think he was almost down there gluing them on. But down at the Cape, when we were getting ready to launch, we were still having trouble getting a thermal protection system working right.